Out there beyond our solar system are distant worlds orbiting alien suns. Not frozen gas giants or lifeless rocks, but planets that might have oceans, atmospheres, even life. These are the most habitable exoplanets, worlds in the perfect zone where water could flow and life, as we know it, might take root. Over 5,000 exoplanets have been discovered so far, but only a handful lie in that narrow Goldilocks range. Some orbit stars like our Sun, while others circle tiny red dwarfs. Each one tells a different story and holds a different mystery. So join me on this journey across the galaxy as we uncover the most promising places for life beyond Earth. From super-Earths to High-Cean worlds, this is where science meets possibility, and where the search for our cosmic neighbors truly begins. In the darkness beyond our solar system, there are worlds orbiting distant stars. Not gas giants or frozen rocks, but planets that could, in theory, host life. Planets that may have oceans, atmospheres, and warmth just like Earth. These are the exoplanets in the so-called habitable zone. Not too hot, not too cold. The conditions, at least on paper, are right for liquid water. And where there is water, life as we know it might follow. The search for these planets is one of the most ambitious quests in modern astronomy. We have now confirmed over 5,600 exoplanets. They come in every size, every composition, every orbit imaginable. But only a tiny fraction lie in that narrow Goldilocks range. Astronomers use telescopes like Kepler, TESS, and Spitzer to find them. They watch for tiny dips in a star's brightness. Each dip could mean a planet has passed in front of its host star. From that small change, we can calculate the planet's size, orbit, and distance from its star. If it's within the habitable zone, it becomes a candidate, a place that might support liquid water and maybe more. But habitability is more than just distance. We need the right atmosphere. We need the right surface conditions, composition, and stability. Some planets orbit red dwarf school, small stars that last trillions of years. Others orbit stars like our Sun. Each case offers different challenges: radiation, tidal locking, flare activity. All of these can affect whether a planet can truly be called habitable. Still, there are worlds that stand out, places that, from everything we've measured, seem promising. One of them is Kepler-4 for 2b. It lies about 1,200 light-years from Earth. It's a rocky planet about 1.3 times Earth's size, orbiting a K-type star. Its position puts it firmly in the habitable zone. It receives just the right amount of stellar energy, and it likely has a stable orbit and surface temperature. It's what we call a super-Earth, larger than Earth, but still likely to have a solid surface. And its parent star is quieter and longer lived than the Sun, which means more time for life to develop if conditions are right. Another strong candidate is Kepler-4 5b. This one is sometimes called Earth's cousin. It's about 1,400 light-years away and orbits a G-type star similar to our own Sun. It's larger than Earth and orbits once every 385 days. It lies well within the habitable zone, but its age, around 6 billion years, suggests any life there could be significantly more evolved. The atmosphere is still a mystery, but the surface gravity and energy input suggest possible Earth-like conditions. It remains one of the most talked about habitable candidates. Then there's Proxima Centauri b, the closest potentially habitable planet to Earth, just 4.2 light-years away. Orbiting the nearest star to the Sun, it's roughly Earth-sized and lies in the habitable zone. but its host star is a red dwarf. These stars emit strong solar flares that could strip away atmospheres. This poses challenges for life, but not impossibilities. If Proxima b has a strong magnetic field and dense atmosphere, it could retain habitability, and being so close, it's a top priority for future missions. The Breakthrough Starshot project aims to send probes there in the coming decades. Also, high on the list is TRAPPIST-1e. It's part of a remarkable system with 7 rocky planets, 3 of which lie in the habitable zone. TRAPPIST-1e is considered the most Earth-like of the group. It's about 40 light-years away, and unlike many red dwarf systems, TRAPPIST-1 shows lower flare activity. This increases the chances that its planets might retain stable climates. TRAPPIST-1e has a mass and radius close to Earth, and it may support a temperate atmosphere and liquid water. Its proximity and planetary diversity make it a key target for upcoming telescopes. One of the most promising is the James Webb Space Telescope. It can analyze starlight that filters through a planet's atmosphere during transit. This tells us what gases are present on, whether they include biosignatures. Biosignatures are molecules like oxygen, methane, and ozone. On Earth, they're associated with life. If we find similar chemical fingerprints elsewhere, it could be the first indirect evidence of biology. Other planets under study include LHS 1140b, TOI 700d, and K218b. Each has unique properties, massive water content, Earth-like gravity, or potential atmospheres. They represent different categories of habitability. K218b, for instance, may be a Hycean worlder water-rich planet with a hydrogen-dominated atmosphere. Recent observations even suggest possible carbon-based molecules in its skies. This opens the door to types of life different from our own, but none of these planets have been confirmed to host life. They are candidate places with potential, and each new discovery helps refine our search. We are entering an era of atmospheric analysis, not just detecting exoplanets, but studying their chemistry, pressure, and temperature. It's the beginning of comparative exoplanetology. Upcoming missions like Ariel, Louvois, and Habix are designed to take this even further. They will survey hundreds of worlds, and some may return spectra unlike anything we've ever seen. For now, Earth remains the only known world with life. But that could change with a single spectrum. One chemical signature from an exoplanet sky, everything shifts. Before we can study habitability, we need to find the planets. Most exoplanets have been discovered using 2 main techniques: transit photometry and radial velocity. Each method tells us something different about a distant world. Transit photometry looks for tiny dips in a star's brightness. When a planet crosses in front of its star, it blocks a small portion of the light. Measuring that dip gives us the planet's size and orbital period. The Kepler Space Telescope used this method to great success. It stared at more than 150,000 stars, watching for these regular dimming events. Thousands of planets were confirmed this way. The other main technique is radial velocity. It detects the slight wobble in a star's motion caused by an orbiting planet's gravity. This method helps determine the planet's mass. When we combine these 2 methods, we get both the planet's size and mass. That allows us to calculate its density and whether it's rocky, gaseous, or something in between. Rocky planets are more likely to support life, but finding a planet in the habitable zone doesn't guarantee habitability. That's why scientists developed the Earth Similarity Index, or SI. It's a scale from 0 to 1 that estimates how similar a planet is to Earth. A planet with an ESI of 1 would be an Earth twin. Anything above 0.8 is considered very Earth-like. The score is based on radius, density, surface temperature, and escape velocity. Kepler-4 for 2b scores above 0.84, Kepler-4 2b, TRAPPIST-1e, and TOI 700d all rank highly as well. These values don't prove habitability, but they help narrow the list. There's also the Planetary Habitability Index, or PHI. It considers more factors, like a planet's chemistry, stable substrate, and energy availability. It's broader but also harder to calculate with limited data. New missions are expanding how we assess these planets. The James Webb Space Telescope has already begun scanning exoplanet atmospheres. It uses spectroscopy to reveal which molecules are present. When a planet passes in front of its star, some starlight filters through its atmosphere. That light carries the fingerprint of atmospheric gases. By analyzing these spectra, we can search for water vapor, carbon dioxide, and even methane. The presence of multiple biosignatures together is more compelling. Oxygen and methane, for example, don't coexist naturally without biological processes. Finding both would be a major clue, but false positives are possible. Volcanic activity or photochemical reactions can mimic biosignatures. That's why context, stellar type, planetary chemistry, system age is essential. We're also looking at how stable a planet's climate might be. Planets with large axial tilts or highly elliptical orbits may suffer extreme seasons that could make life harder to sustain. Tidal locking is another concern. Many planets around red dwarfs keep the same face to their star. One side scorches while the other freezes. But some simulations suggest tidal-locked planets could still be habitable. If they have thick atmospheres or oceans, heat can circulate. That creates a narrow band of life-friendly conditions along the terminator zone. The most exciting part is how much more we're about to learn. Next-generation telescopes like LOVOIR and HABEX will image exoplanets directly. They'll block the light from the parent star to see the planet beside it. This technique, direct imaging, has already captured a few massive exoplanets, but upcoming instruments will allow us to target Earth-sized worlds. For the first time, we'll be able to see pale blue dots around distant stars. These missions will also measure polarization, how light reflects off different surfaces. Oceans, clouds, and vegetation all scatter light in specific ways. With enough sensitivity, we may even detect surface features, clouds on another world, a glint of reflected ocean, maybe even seasonal shifts in color. All of these are long-term goals, but within reach. The technology exists or is in development, and the search is accelerating. For now, we continue scanning, watching, calculating. Every month, new candidates are added to the habitable planet list. Many are quickly ruled out, too hot, too cold, too irradiated. But some linger in the data, waiting for deeper study. Each one could be the first world we confirm as truly habitable, or even inhabited. All it takes is one detection, a clear signal from across the void. The search for life beyond Earth depends on one thing above all: chemistry. Life changes its environment in measurable ways. On Earth, it fills the atmosphere with oxygen, methane, and complex organic gases. These chemicals don't exist in isolation. They interact, overlap, and create patterns that only life sustains over long periods. Astronomers call these patterns biosignatures. A single gas is rarely enough. Methane, for example, can come from volcanoes or hydrothermal vents. But methane, combined with oxygen sustained over time, points to biological processes. The James Webb Space Telescope is beginning to search for these signs. Its instruments can isolate specific wavelengths in exoplanet atmospheres, and some early results have already sparked attention. One of them is K218b. This is a potential high-seen worlder planet with a deep ocean and a hydrogen-rich atmosphere. Recent data suggests carbon-based molecules like methane and possibly disulfide, a gas on Earth produced only by life. If confirmed, it would be the first indirect detection of a possible biosignature on an exoplanet. But the signal is faint, and scientists urge caution. Follow-up observations are needed to rule out non-biological sources. Other biosignature candidates include ozone, nitrous oxide, and combinations of water vapor with organics. But interpretation depends on the planetary context. Different stars produce different radiation levels, which change how atmospheres behave. That's why red dwarf systems like TRAPPIST-1 require special modeling. Their planets may have atmospheres shaped by ultraviolet flares and tidal locking. Even with biosignatures present, it could be hard to tell if they're biological. So scientists are also developing false positive frameworks. These are checklists of conditions where lifelike chemistry could emerge from lifeless processes. By ruling these out, we increase the reliability of detection. Parallel to this, we're exploring abiotic pathways, chemical routes that mimic life without any organisms. For example, water vapor and methane could result from planet formation, not biology. Temperature, pressure, and stellar history all play roles. Still, there are atmospheric combinations that are hard to explain without life. Earth's own spectrum, viewed from light years away, would show a signature of active biology. That's the kind of pattern we're hunting. And it's not limited to Earth-like conditions. Life may arise under different chemistries, pressures, and temperatures. Some scientists are exploring non-carbon-based lifelike theoretical forms based on silicon, ammonia, or even plasma. But carbon remains the most promising base. Its chemical versatility is unmatched, and it forms the backbone of every known life form on Earth. That's why most biosignature research focuses on planets with liquid water, carbon chemistry, and stable climates. These conditions don't guarantee life, but they provide a familiar framework. It's a place to start. Theories about life's origins also play a role. If life began quickly on Earth, within a few 100 million years, it might be common elsewhere. But if it took billions of rare events, we might be alone. We don't know yet, but exoplanet statistics help frame the possibilities. More than 1 in 5 sun-like stars may host an Earth-sized planet in the habitable zone. That means there could be billions of potentially habitable planets in the Milky Way alone. Even if only a tiny fraction host life, that's still thousands, maybe millions of living worlds, and we've only just begun to search. The next leap will be direct detection. Not just atmospheric gases, but signs of photosynthesis, seasons, or even surface vegetation. Some scientists call this the red edgier spectral shift caused by chlorophyll reflecting near-infrared light. On Earth, satellites can see this edge. From space, a similar signal from another world would be extraordinary. It would suggest plants or something like them cover the surface. Another target is night-side illumination. If a planet's dark side emits unusual light patterns, it might mean cities, technology, or fire. This is speculative, but technically measurable with future telescopes. These would be technological signatures, rather than biosignatures, signals of advanced civilizations, rather than microbial life. The search for both is happening simultaneously. Programs like SETI still scan the skies for radio signals, but exoplanet research is opening new ways to detect intelligence indirectly, from pollution in atmospheres to unnatural heat signatures. For now, we focus on the basics: water, air, and organic chemistry, because life as we know it is still the clearest target, and it's one we may be on the brink of discovering. We've identified the targets. Now we're building the tools to go deeper. A new era of exoplanet exploration is already beginning. The James Webb Space Telescope is only the first step. It can detect biosignatures and study planetary atmospheres. But it won't be the last telescope we send into space. Next comes Ariel, launching in the late 2020s. It will analyze the atmospheres of hundreds of exoplanets. Its focus is not on detection, but on population-level understanding. Then there's LoveWeather, Large UV, Optical IR Surveyor. It's a concept mission designed to directly image Earth-like exoplanets. If approved, LoveWeather could see distant worlds as tiny pale dots beside their stars. Another is HABEX, short for Habitable Exoplanet Observatory. It would include a large telescope paired with a Starsheeder separate spacecraft that blocks starlight, that would let the telescope see the dim glow of a planet right beside a blazing star. These missions aim to do what none before have done. Not just find Earth-like worlds, but image them, analyze them, and characterize them. They may reveal blue skies, cloud systems, and perhaps hints of continents or oceans. The data they return could be transformative. An atmosphere rich in oxygen and methane, a surface with seasonal color changes. Each piece of information brings us closer to a confirmation that life is not a miracle of Earth, but a function of the universe. Something that happens when the conditions are just right. But looking isn't enough. One day, we may want to go. That idea, once science fiction, is becoming a serious conversation. Projects like Breakthrough Starshot are exploring how to send probes to nearby star systems. The concept involves ultralight nanocrafts pushed by ground-based lasers to a fifth of the speed of light. At that speed, a probe could reach Proxima Centauri b in just over 20 years. The probe would carry sensors, cameras, and communication devices. It would fly past the planet, take images, and send the data home. It would be humanity's first interstellar flyby. There are enormous technical challenges. Building a light sail that survives acceleration. Targeting a planet trillions of miles away with near zero margin for error. But the engineering is being explored now, and the drive is simple. We want to see what's out there up close. Even more ambitious concepts propose fusion-powered craft or antimatter drives. These technologies could enable crewed missions in the distant future. But for now, the goal is information, not colonization. Meanwhile, Earth-based observatories are getting smarter. Giant telescopes like the 30-meter telescope and the extremely large telescope will use adaptive optics. These systems correct for Earth's atmosphere in real time, giving sharper views of distant systems. With these tools, we may detect exomoons, measure planetary rotation, and even identify weather patterns. Each discovery builds a more detailed picture, not just of planets, but of potential homes. Because that's what the habitable zone implies. A world that's not just Earth-like, but livable. A place where chemistry can turn into biology. As the data grows, so does our confidence. We may already have found the first living planet beyond Earth. We just don't know it yet. And the answer could be hiding in a spectrum, waiting to be decoded. What began as a faint dip in starlight has become a revolution in planetary science. We're building a library of worlds. Some dry, some hot, some icy, but some just right. Some with conditions that mirror Earth's in uncanny detail. Oceans the size of continents. Clouds that form in bands like Earth's own skies. The journey to find these planets has redefined our place in the cosmos. We now know Earth is not alone in its potential. The universe is full of possibility, and somewhere perhaps not far from here there may be a world where the night sky includes our sun, faint, distant, a speck of light in their own search for others. The search for habitable exoplanets has grown from theory into precision science. We've moved from guessing to measuring, from imagining distant worlds to cataloging them by the thousands. We now understand the key ingredients for life as we know it: liquid water, a stable atmosphere, the right balance of temperature, pressure, and chemistry. We know where to look, around stars not too different from our own, at planets not too big, not too small, just right. We've found super-Earths, high-Ceon worlds, and temperate exoplanets that orbit quietly around dim red dwarfs. We've begun reading their atmospheres like fingerprints, and in a few rare cases, we've seen hints that something extraordinary might be happening there. But so far, there is no confirmation, no smoking gun, no molecule or pattern that definitively proves life exists elsewhere. This is not failure, it's progress. In science, ruling things out is just as valuable as finding them. We now know that habitability is rare but not impossibly so, that Earth-like planets may be common in number but complicated in detail, and that our tools are finally sharp enough to notice. We've learned that life depends not just on a planet's position, but on its past, its atmosphere, its host stars' behavior across billions of years. We've also learned that alien life may not be like us at all. It may thrive in oceans beneath icy crusts, or in dense atmospheres warmed by tidal forces instead of sunlight. It might breathe something other than oxygen. It might not breathe at all. It may not even be made of carbon. These are the new frontiers of astrobiology, where chemistry meets possibility, and where every discovery expands the definition of life. There are still questions we can't answer yet. How common is life once conditions are right? Does it form Isilure only with incredible luck? How long does it last? Can it survive catastrophe? And could we recognize it if we saw it? These are not just scientific questions, they are technical ones. They depend on better telescopes, deeper surveys, and more precise instruments. Each mission we launch brings us closer to answering them. The roadmap is already drawn. New observatories will scan thousands of planets. Some will focus on rocky Earth-like worlds. Others will map atmospheric chemistry in real time. Soon, we may see the light of another living planet. A world where water flows, where clouds drift, where chemistry crosses the line into biology. And when we do, it will not feel like science fiction. It will be data, measurable, repeatable, real, and it will change how we see everything. Earth will no longer be unique in its biology. Life will become a cosmic property, not a planetary one. That moment may come quietly. A spectrum, a signal, a peer-reviewed paper buried in a journal, or it may come all at once. A cascade of confirmation. The first true detection of alien life, waiting across a sea of stars. Until then, we keep listening, we keep watching, we keep building, because the universe is wide, and we are curious. And somewhere out there, the conditions for life may not just be possible, they may be thriving. All it takes is one planet, one signal, one undeniable sign that life exists beyond Earth. And when that day comes, the search will not end. It will begin again with new questions, bigger telescopes, and even deeper skies, because we will finally know we are not alone.